Oh, we are past time, right? What time is it now? Oh, yeah, sorry. So let's just start. Okay, so let's see. We are going to next thing is oscillatory integrals. So what's the issue here? So far we studied so exponential integrals which are real. So exponential integrals of this form are the exponential of minus 1 over h bar s of x dx, right? So the action is always real, no matter what. So yeah, so we discussed that this sort of exponential integrals come up very often in Euclidean quantum field theory, where we use positive definite metrics in Euclidean QFT. And also, they appear very often in statistical mechanics and statistical field theory, because this is like a partition function in field theory, in a stat make, etc. So these are kind of useful, and also, yeah. But the actual Feynman integrals are not like this. There's an I in front of the thing. So the actual Feynman integral is of a different form. It's similar to this, but it's integral over, I don't write over what, e to the minus I over h bar s of x dx, right? So there is this crucial number I in front of the thing, the rest is, so this is pure imaginary in the exponent, right? So as we discussed, this number, right, has absolute value 1, and even over R, this is the divergent. Usually, this is, I mean, so let me give you simplest example of this. It's a famous Fresnel integral. Fresnel integral. This was introduced or came across with, in the work of Fresnel in 1820s in wave optics. Right? So what is this Fresnel integral? In the simplest case, we have, well, it is just this one, really, integral over R, for example, exponential of I x squared dx. Right? It's such an integral. And of course, this is absolutely divergent. The integral is absolutely divergent. Because absolute value of this guy is 1. So you're integrating 1 if you want to do it by absolute convergence. You're integrating 1 over R, so this is divergent. Okay. However, these guys are conditionally convergent, and that's the important difference. But conditionally convergent in the sense that the limit minus r to r exponential of I x squared dx as r goes to infinity. This limit exists. You can show that the limit exists. So just to give you an idea how the proof goes, because this is kind of nice to work it out, at least in one example. So proof. So the proof, I mean, okay, it's clear that to prove this is enough to show that this integral 0 to infinity, or I would say 0 to r sine of x squared dx, the limit of this guy as r goes to infinity exists. Right, because this is the real part of the, I mean, this is the imaginary part of this. And the same, if you prove this, you can also prove for cosine of x squared, and that follows. And to do this, we can just, it's enough to prove that actually integral from 1 to r goes to infinity, exists. And how do we do that? Well, I mean, this is calculus, really first year calculus problem. So the proof is by integration by parts. An interesting calculus problem. There is integration by parts, because I can just we can just do the following, right? We can just write in integral 1 to r. I can just say, okay, I just introduce what? Yeah, 2x here, sine of x squared times dx over 2x. And then we call this part, I don't know, dv, and this part as 1 over 2x as u, right? 1 over 2x equal u. So this is going to be equal to uv, which is 1 over 2x. I believe is minus cosine of x squared from 1 to r minus integral from 1 to r. So yeah, this is u dv is a u minus v du. So and then yeah, so I get minus 1 over 2 x squared, and then negative cos of x squared. So this negative cancels cos of x squared dx, right? So we got to that. Okay, so then it's clear that the integral is convergent now, because this at one end goes to 0, and at 1 you just evaluate. It's not a problem. And here we can, now this one is absolutely convergent because you can estimate it by 1 over 2x squared. Its absolute value is less than 1 over 2, and that's convergent. So this is convergent. So that's the end of the proof using integration by parts. So in fact, you can extend this more general case. Basically, I can say in general, integral over r exponential of I p of x dx, where p is a polynomial of degree bigger than or equal to 2. Degree of p bigger than or equal to 2. It's a polynomial. Although, I mean, it can be extended to more general class of functions than polynomials by looking at the growth at infinity, but that's okay, we don't need that. if P is a polynomial whose degree is bigger than 2, this integral is conditionally convergent. Conditionally convergent. You got it. Okay. By the same, you can use the same technique, integration by parts. Yeah. Just be careful a little bit. That's how it works. Okay. Yeah. So, but the problem. So these are called oscillatory integrals, and it's good to understand actually why these things converge, because it's very strange, right? This guy has absolute value 1. I mean, not absolute value 1. I mean, the exponent, the complex version, but this guy goes up to, it doesn't decay, this function at infinity. It just oscillates between 1 and -1 all the time. So it sounds very strange that although it's not decaying, but it still is convergent. It's good to think about it. So the reason that's usually offered is that it oscillates, but the length of these oscillations, actually, the distance between two jumps gets smaller and smaller. So the function actually, like if you draw the sine of x squared function, is actually okay. So it's just like unlike sine function that keeps the distance between zeros, the distance between zeros goes to 0 actually, in the order of, I believe, maybe 1/2x or something, 1/x in that order. So this is usually, and so there is a cancellation. There's a lot of cancellation between positive, negative. So at the end, there is a finite contribution to this, for example, to the Fresnel really did not look at these things as complex functions, just sine of x squared and cosine of x squared. He evaluated both integrals to be, I believe, pi/4 or something. We can also evaluate it now. So okay. I mean, I'm not very satisfied with this understanding still. I try to understand it in a better way, but I don't know how. I mean, it's kind of it's good to think about it, why this is really convergent. I mean, we did this trick, of course, but this really, I think, hides some deeper facts here, probably. Yeah. Okay, so that's enough. But there is a difficulty with this integrals, and the difficulty is the following. So imagine you want to show that the following function, for example, f of z equal to integral over r exponential of I, for example, x cubed plus zx dx. Right? Okay, I mean, this function obviously exists, is defined for any z, right? Even complex numbers. This integral is conditionally convergent for any complex value z, right? So you get a function of z in the complex plane if you integrate out x. Now, you want to show that, for example, this is a continuous function of z, or differentiable function of z. You want to show that this is differentiable. So the question is how to show this f is differentiable, how to prove f is differentiable, etc. I mean, you want to know some properties of this function. This function just exists is not enough, right? I mean, you want to do something. For example, you want to show that it satisfies some differential equation and stuff like that. And this conditional conversion actually stops us from doing integration, from doing differentiation, changing differentiation and integration. We cannot do that. You're completely stuck with this integral. Even proving that this is continuous is quite difficult, actually. Although it's a well-defined function, but no. So working with this kind of things mathematically using just conditional convergence is very difficult. And that's where the new idea is needed, and this new idea is contour deformation. So we're going to deform the contour deformation and use complex analysis to the rescue. Okay. Okay. So this is contour deformation. And complex analysis. So this works like magic. I mean, when you think about it, it's really amazing that we have this technique available. So what do I mean is the following. So e.g. for this integral, r exponential of I x squared over 2 dx, right? Okay, so originally we argued in the distance in the interval minus r to r, right? Now we're going to deform this contour by going into the complex plane. We rotate it by 45 degrees. We get into this thing. So this is the original direction. This is new direction. And this is also new. Right? So this is my contour with its orientation as well. So it goes here, there, right? And so this function e to the I, so let me put it like z squared now over 2. This is holomorphic in z, right? This is holomorphic in z. So because this is holomorphic in z, so it means that the integral over this closed contour is 0. So I call this whole closed contour C. So integral over C e to the I z squared over 2 dz is equal to 0. And then what we can do, we can just say that, so integral, what is this guy? This is integral minus r to r. So basically what we're saying is that lim of this guy plus integral, this is like C1 plus integral C2 plus integral C3 is equal to 0. We have 4 contours. I mean, forming the closed contour. C is the sum of, well, I mean, this is C0, C1, C2, C3. Now we can show that as r goes to infinity, this guy, this part goes to 0 actually. There's a little bit of calculation, but you can show that. So the integration over this goes to 0. So integral over C1 and integral over C2 both goes to 0 as r goes to infinity. I mean, you have to do a little bit of estimate here, right? Because here, I mean, the length of the contour goes to infinity as well. But the approach of this guy to 0 is faster than the increase of n. So it follows that the limit of this guy is actually minus r to r. What we want to compute, r goes to infinity, is actually equal to integral over this line, over this infinite line, L. So we have to evaluate this integral now. So this is the Fresnel integral that we want to compute. Now we can compute it as this integral here. So let's see what happens if you go over this line. Right. So if you go over that line, L, so integral over L, exponential of I, z squared over 2dz is equal to, okay, so I just say integral from minus infinity to infinity. So we can parameterize this curve as t plus it, right? This curve we can parameterize as t plus it, t from minus infinity to infinity goes like that. So then this becomes e to the I times t plus it squared over 2. And this dz is, well, this is z, right? Dz is dt plus I dt, which is 1 plus I dt, right? So this is equal to integral minus infinity to plus infinity I times, so this is t squared minus t squared, they cancel. And I've got, so this is 1/2. Then 2it squared remains from the interior. 2it squared. And this is exponential. And I've got here times 1 plus I dt done. Okay. So now something interesting happens. This I and I gives me -1. So I've got here integral minus infinity to plus infinity exponential of negative t squared times 1 plus I. Well, I just keep that 1 plus I outside now. That's okay, it's a constant. I think so. I can pull it up. And then this is dt. Right? And this is a Gaussian now. So this integral, which was not Gaussian, was extremely oscillating. If we deform the contour like that and we show that these things go to 0, it becomes a rapidly convergent integral. And all the arguments of differentiating under integral sign and all this actually work now. Okay, so, and of course, this is, so we can evaluate even the value with 1 plus I. What is the value of this thing? Here is minus, how to say this? Okay, so we have exponential of minus a over 2x squared dx was root 2 pi over a, right? A is equal to 2, so this is equal to root pi. This is root pi. Right. So this not only actually proves convergence, it allows us to do those sort of calculations, to do the integration, as we'll see on differentiation under the integral sign. And also, in this case, evaluates actually exactly the integral. So that's the idea. With oscillatory integrals, the idea always is to find a good new contour over which things actually become rapidly convergent. So basically, we are turning an oscillatory integral into a real integral, which is fastly convergent. That's the idea.
But how do we get an real integral?
What? No. Okay, yeah. Right. So that's the idea. Now, so we looked at Fresnel. Now let's yeah. Right. Okay, we looked at the Fresnel thing now. So there's another very famous oscillatory integral which is called Airy integral. So second example. I'll give that example. Right. Questions? There's no question. Okay. So Airy function. This is called or Airy integral. It doesn't matter. Same thing. So this function at AI of z is equal to 1 over pi integral from 0 to infinity cosine of so let me write it like this: t cubed over 3 plus zt dt. Okay. But what we did actually about cosine of polynomial functions oscillating, this is an oscillatory independence conversion, right? So this is conditionally convergent. For all z belonging to C, complex numbers. So Airy actually considered this, Airy, in 1830, what year I have here? 1838. In a famous paper, it's called, what's the title? It's called Intensity of Light. You see, this again comes from the optics. Intensity of light. Near caustics. So basically, Airy's point was that he derived this function and he showed that absolute value of AI z squared. Well, actually, for him, z was only a real parameter. He didn't go over the complex numbers. For him, he needed just z belonging to R. Is the intensity of light, the square is the intensity of light. What he was doing, he was studying rainbows. And in the study of rainbow, they observed, okay, so you see the principal spectrum, you know, when you see the rainbow, you see, I don't know, velvet, I don't know, yellow, red, you know, all these colors. But then some strange things also below those standard things appear. So after the visible range, there are some dark spots. Okay, there are some other lines that come, and there are some dark spots. So those dark spots, according to Airy, corresponds to zeros of Airy function for Z negative. And these are the intensity of light near caustic. So this is the caustic, I mean, for example. And these zeros are, well, Airy showed that actually this is the intensity of light. Yeah, so these are the zeros. So let me write it here. Zeros of they are Z for Z less than zero. Of course, we are talking about real numbers. This is the x-axis. Uh, correspond to dark points in the rainbow below the caustic. Well, I'm not an expert. Don't ask me what is caustics because it's fancy optics. I'm not an expert. I mean, so if you know, just tell me. But I know this paper is very famous, and so the point is that they could measure this thing. So they measured, I don't know, maybe first few of them. Airy could measure himself, but then there was another guy who measured 50 of them, hundreds of them. So there are many, many zeros. And Airy was very interested in showing this by calculating zeros of Airy function for negative values of Z. Now maybe I put here Z. But again, this integral is extremely difficult to work with, to do anything with, because it's only conditionally convergent. So eventually, the person who actually broke this mystery of this to a large extent was Stokes. So before going to that, I don't think we'll get to work on Stokes today, but let me tell you two facts about the Airy function that we know, and then we'll see. So first of all, two facts about the first fact is that AI of Z is actually a holomorphic function in Z. Is holomorphic Z, which again, as I said several times today, is very difficult to prove actually using this definition because you cannot differentiate this function. It's illegal to differentiate this. Okay, so that's one thing. Second, I mean, this was observed by another mathematician. It's so second is that AI is a solution of the differential equation. AI Z is a solution of this ODE y double prime minus zy equal to 0. So it's a second order homogeneous ODE in the plane. And the claim is that this actually, yeah, satisfies the Airy function, satisfies this. And because we cannot differentiate, so it's very hard to verify this by original method, original definition. Okay. So how to, first of all, prove that this guy is holomorphic? Again, we do a contour deformation, and this will help us to replace this definition by another definition, which is very transparently becomes holomorphic. So idea then is first is contour deformation. So, of course, so you see, when you have this real axis like thing, you can deform it to many things, right? There's not one other curve that you can deform to. I mean, what is the natural choice? We should deform it to what? You have options actually to deform to. And which curve to deform to, there are some curves that are better than the others. All right. So, but for now, we'll just choose one deformation. And for what we want to do is okay now, but this is not the optimal. So a non-optimal deformation. In this case, we just, this is the r-axis, on the x-axis, we just deform to a straight line, which stands at distance delta above the x-axis. And so we look at integration along here, 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 and back here, right? So first of all, this integral, of course, you can write it as a integral over r. So this I of z is equal to integral over r. I want to write it as a holomorphic function, right? So e to the I t cubed over 3 plus zt dt. And there is, I have to put 1 over 2 pi now. You see, the idea is that the odd part, I mean, the imaginary part actually is 0 because that's a sine function, a sine of this, and because of oddness of this sine function. And so odd powers only, so that's 0. And the cosine function is even, so it takes positive, negative value, they give us twice this value. So this is okay. Now, but the good thing is now this is a holomorphic function in the plane. So again, I can say that the integral over the whole thing is 0 now. So this is, let's call this L delta. So C1, C2. So integral over C1 and integral over C2, these two parts go to 0. Again, this is a little bit of calculation. It's not so bad in this case, actually. The Fresnel is more difficult. The Fresnel case. But this is not so bad. Okay, so then it follows that actually the integral ai of z, really, I call this whole thing, so it's integral over L delta exponential of I t cubed over 3 plus zt dt. Yeah, so now what is good about this, we have to still see if it buys us anything by doing this or not. So if you parameterize this, so let's call t equal to x plus I delta. I just parameterize the curve above I delta x stand infinity, minus infinity. Right. So then I have to evaluate that cubic term over there. So I times t cubed over 3 plus zt is equal to, okay, so I have to calculate that now. Yeah, I did the calculation. So this is actually equal to, it comes out to be negative. You raise this to power 3 and sum, it comes to negative x squared delta plus delta cubed over 3 minus z delta plus I times x cubed over 3 minus x delta squared plus zx. Okay, so this is the real part of the guy here. And this is the imaginary, obviously. So the point is that the now absolute value, so if I call this f of t, absolute value e to the I f of t is actually essentially a Gaussian function with rapid decay at infinity now. So this is equal to, exponential of negative x squared delta plus delta cubed over 3 negative z delta. Okay, so then you can see, because delta is positive, you should not deform it to the below, because if you deform to the below line, you get disaster, something which is very messy again, going to be only conditionally converged. But so now this is a rapid decay integral at infinity, exponential decay, and these terms doesn't matter because this is the dominant thing. And this is a purely imaginary thing, so it doesn't contribute to convergence or divergence. So we are done. So this conclusion then is that really AI of Z not only is well defined, it's actually a holomorphic function itself, because this integral is holomorphic itself. You can just, it's holomorphic itself. This is that. And then you can differentiate under the integral sign. Okay, so it's a bit longish, this calculation, but we can do it by hand. And then you show that it satisfies this Airy differential equation. So this is called Airy or Stokes differential equation, something like that. So yeah. But as I said, this is not the optimal, this is the best possible deformation. We may get back to how to choose the best possible deformation, because then we can use the saddle point method to write better approximations for this. For now, this is okay. Now, okay, let us look at the behavior of Airy for negative and positive real axis. See if we can infer something about that behavior actually by just so this is a kind of ballpark estimate now. Of behavior. Z for Z positive and Z negative. And the guiding principle here is this differential equation. Now, so this differential equation, okay, I mean, it doesn't have a closed form solutions because this is it's linear, but it's complicated. This differential equation. However, if we are for z positive, we can freeze the value of z, right? For z positive, freeze z, do something like omega. And if you look at the solution of y double prime minus omega y equal to 0, this you see that it has two solutions, root omega t and z and minus 1. So the general solution in this case, y of z is equal to alpha e to the root omega z plus beta exponential of negative root omega z. So it's an exponential function. So it's not oscillatory for z positive. In fact, this area function, I mean, it's not a proof. This is just a kind of estimations and some feeling. I of z is rapid decay. So it's this branch is rapid decay for z real and positive. So it actually looks like this. Yeah, it goes to 0. We are not proving it now. To prove it, we have to do some more delicate contour deformations. But let's just. And for z negative, yeah, if omega is negative here, then you get sine cosine function solutions, right? You get oscillatory functions, sine cosine functions. And so this function, you can guess that a function is going to be oscillatory for z negative, and in fact it is. So this comes back, and then you get zeros. And it decays, and the zeros actually approach. Now, okay, I don't know really if the zeros really pile up, the distance between zeros go to 0 or what, but this is completely known. And these zeros have been calculated, many of them, to high precision. So because of Airy's work, this was important for intensity of light and all this. I don't know, for example, where is the first zero? I forgot. These are vastly available. So this function, then, this Airy function is it's not just any function. It's actually, well, if we ever do WKB, approximation in quantum mechanics, near turning points, the behavior of the solutions are almost like this. So this is a first order approximation to some general solutions for second order ODEs that showed you the equation near turning points. So what does this mean? It means that any function like plays the role of harmonic oscillator, quantum harmonic oscillator for this sort of WKB stuff. So it's really a universal object. It's not just one function among many. I mean, it has a feature which is very, very universal. But this we cannot even touch it now. We just discussed.
So the
question.
We are fixing like z to be omega here, but in reality we are looking for the asymptotics, right?
Right. Yeah.
So
yeah.
Like, is it like valid to just fix something?
No, this is not an argument. No. This is just somehow to get us some feeling for the thing. No, it's not valid. Yeah. And in fact, you're quite right. We have to get some asymptotic expansions, which is not obvious from the definition or this definition. So asymptotic expansion comes from another consideration. Yeah. And then we know how it behaves near it. And actually, how it behaves. Yeah, so in this sector, it behaves like this. In other sectors, it behaves quite widely, actually. So at infinity, every sector near infinity, this has very wild different behavior. but this is known. Basically, I believe there are only 3 types of behavior, but they are different. Yes. Yeah. Okay. So what I wanted to do next is okay. So what's the punchline here? So we had the Laplace method before. In the complex case, we have this analog of Laplace method, which is called the stationary phase approximation. So let me just write it down. So let me see if there are questions in the chat. No. So the complex, okay, so complex analog. First method. This is called a stationary phase approximation. It is very useful and interesting. Basically, we want to say that, yeah, an integral of the form a to b e to the I don't know, maybe I'll just write it as s of x, yeah, over h bar. It's like oscillatory integral that we started, dx. Can always be written as, yeah, h bar to the power half, e to the I s of c over h bar times I of h bar, where I of h bar is a smooth function in h bar bigger than or equal to 0. In h bar bigger than 0. C is the unique non-degenerate critical point non-degenerate critical point of S of x in AB. So we have chosen this interval AB is small enough such that there's only one critical point. You see, now we are not talking about maximum or minimum. We are just talking about critical point, a critical point. But that is unique. Because so the second derivative can be positive or negative, doesn't matter. And that's one thing. And yeah, right. So now about I of h. So I of h, we can write it as in by Taylor's formula. I of h is equal to yeah. So right, I of 0 plus h bar. Yeah. Right. So let me write it like this. That's not the idea. It's just a0 plus a1 h bar plus a2 h bar squared plus 1. So this is the asymptotic expansion. And I of 0, that's the only part that we can say something about just easily, I of 0 is equal to, remember in the real case where we had actually in a minimum with second derivative positive, it had to do with the square root of the determinant of the Jacobian at that point, Hessian at that point. There's a similar expression here. So I of 0 is equal to root 2 pi e to the plus minus pi I over 4 e to the plus minus pi I over 4 times 1 over root. Now I have to be careful. I just put a double prime at C, right? The Hessian of the function at the critical point. This is plus minus. So plus, if the derivative, a second derivative is positive, I believe so, and minus if second derivative at C is negative. It just has to be non-zero, but both are okay. 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 Yeah, this you can see that this is similar to the calculation we did for the Fresnel integral, e to the I x squared. In that case, the function was just s of x was just x squared over 2. And this gives us Fresnel formula for in that case. That, I mean, it's not approximate even, it's exact in that case. And all these higher terms are 0, only a 0 remains if s of x. So, so let me write it e.g. I mean, this is a really cheap example, but that's okay. E.g. s of x equal to x squared over 2 is the Fresnel case. I mean, in the sense that, yeah, this is not even an approximation, it's an exact evaluation. Yeah, so what else I wanted to say for now? Oh yeah, there's a difference between, another difference between this case and the case of real is that actually all critical points contribute. You see, in the real case, there was this smallest critical point, that was the dominant part. That would dominate everything. So in other words, I'm saying for real case, so imagine you have a S of x action which is like that, right? Only this would contribute. Only this C would contribute. You're integrating from minus infinity to plus infinity this S of x. But only this would contribute. The other ones actually are subdominant. But in the imaginary case, you have to sum over all these critical points, non-degenerate critical points. You just sum over, so the sum is bigger, all non-degenerate critical points. It's not that, because these are phases, there's a complex parameter, and it's not that one dominates the other, there's no such issue. They all contribute. So to prove this from that, you can just put them inside things, write the integral over sums of these things, and in between the contribution is minimal, it goes to 0, asymptotically, exponentially small, and you get this result, summing over all critical points from that result. And also another thing is, I mean, there is an obvious generalization to RD. Similar for for integral over RD. I don't write the formula because it's very similar to that. You just have to put Hessian matrix here. This is the determinant of the Hessian matrix and all these things. So, yeah. RD exponential of, again, by the way, it's for similar thing. Right? And that's the stationary phase approximation. Okay. Right. Okay. So, I mean, again, there's much more to be done in this case. I mean, but for now, we are okay. Now, so we can now turn the page, but before doing that, I'm going to say a little bit of things that can happen for the actual quantum field theory case. So this maybe I can say a glimpse of the actual QFT. Well, this is not really actual. It still is a toy model of actual. So it's still toy model. But infinite dimensional. But infinite dimensional. Still toy model QFT. So the ideas that we develop, so all I want to do, I want to show how the ideas that we developed is actually transported into the infinite dimensional situation of quantum field theory. So what are our fields then? So these are, say, smooth functions from circle to R. So our fields are functions on the circle. I mean, like waves on the circle. We can do that, right? Smooth, maybe. These are our fields. And then what is action? Action is S of y. So I have to give you a number for each field, every function, full function on the circle. So this action, they have some conditions in physics that they have to observe. For example, has to be local. They have some general conditions, but then the natural action is basically this one, 1/2, in this case, integral over S1. The derivative of phi with respect to the parameter t, which is parameterizing circle, is absolute value of this square. Well, in mathematics, this has a name. It's called Dirichlet energy of the field. This has, right? I mean, this is what we also call them, maybe. Yeah. Yeah, this is called Dirichlet energy. This sort of things actually were considered by Riemann already. And Riemann was the guy who actually named it Dirichlet function and Dirichlet principle because he attended Dirichlet's lectures in the 1850s while he was doing this. Not this example, but another over Rn and stuff like that. So here, S1, I want this to be R over 2 pi R. So this is a circle of radius R for us. Circle we keep the radius alive. So then what we are interested in is to compute this partition function. We want to compute this partition function, which is z equal to integral over all fields, right? Exponential of -1 over h bar s of phi and d phi. So this is a infinite dimensional space. All functions, it's like a mapping space, function space. All functions from S1 to R. And this is a fictitious measure, which nobody knows what it is, but nevertheless, we believe we can work with it. And this is a finite number that we can keep. So this is an example of a non-interacting field. I mean, quantum field theory. So it's a non-interacting. It's actually free QFT. Interacting scalar field. Real scalar field, I mean QFT. Yeah. So now when you look at this, you say, okay, here's the question. Here's the question. How can I relate this to those finite dimensional integrals I was talking about? I mean, in that case, we had this matrix A or B, non-degenerate matrix B, and we had these perturbations of B with higher rank tensors and all that. Where is B? Where is this matrix B here, for example, and this sort? So that's it's hidden here, and to see what it is, we just have to do an integration by part. It will show it. It will show itself. So so if you just write S of phi, which is equal to 1/2 integral as we did derivative of phi, and this is squared dt. This is actually equal to 1/2. Yeah. Integral Laplacian of phi and phi dt, where the Laplacian of phi, Laplacian of phi is, now I have to see if I mean positive or negative. Okay, negative. This is the geometer's Laplacian, negative second derivative, not positive second. Negative phi. I mean, usually Laplacian, okay, it's first of all, it's one variable, Laplacian, but usually Laplacian is without minus sign. But it's more convenient to use minus sign because with minus sign, it actually becomes a positive operator. If you don't put minus sign, you get a negative operator. That's kind of funny. Okay, so this is the Laplacian. So, yeah, I mean, this is over S1. This is over S1. I mean, this is really amazing. Now this is really beginning to look like what we have. This delta is like our B. Or this is the matrix. So the analogy, and that's very important. So the analogy here is that we had before integral RD exponential of minus 1/2, right? Minus 1/2 d phi Okay, so let me put it like this. Both bxx, bx, right? But B is a positive definite matrix. And here we have integral over fields. So this finite dimensional space is replaced by this infinite dimensional space, and exponential of minus 1/2. Yeah. So we have this integral, right? So phi is like x. Yeah, you see, here, there is a summation involved, right? Here. We're summing over all I and j's here. Here, the summation is over all points on the circle. Is that mean over infinite set? Right? So that's the analogy. So then, by analogy, we are going to propose something which looks crazy, which is not crazy. It's actually all, that's the point of QFT. So we just say that integral, so let me write it here. So by analogy, we just say that integral e to the minus 1/2 s of phi p phi is equal to 1 over the square root of del prime of b. You see, this guy, you remember it was equal to the determinant of root 2 pi over b, right? The 1 over the square root of the determinant of b. Okay, forget about this 2 pi factor. We can't do anything about it. We have to throw it away and argue that, okay, we just throw that away. But, oh, this is the determinant of, determinant of delta. This is our b, delta. So the Laplace, so the point is that Laplacian delta is like b. And that's a very, very important analogy in mathematics and physics. That really goes to the heart of the matter right away. It's an extremely important analogy, extremely deep thing.
That is dead prime.
Yeah, right. So what is that prime now? Okay, so so what is the determinant of Laplacian? Right. So what is that prime? So the idea is, what is determinant for a positive operator like B? It was product of all eigenvalues, right? We have to take all eigenvalues and multiply them. So then we can try to define something like product of all eigenvalues, infinite product, I from 0 up to infinity. But then there's a problem here. The problem is that there is an eigenvalue which is actually 0. It's called 0 mode. There is such an eigenvalue because constant function is killed by Laplacian, and there's multiplicity 1. So if we multiply all of them, then we're going to get 0. That's a cheap thing. We just throw that away, and we put here, and then we start from 1. So product of all non-zero eigenvalues now, right? All non-zero eigenvalues. But this doesn't make sense because in practice, this is divergent. For any Laplacian operator on manifolds, or any Laplacian. on manifolds. I mean, so to convince ourselves, actually they go to infinity. Always they go to infinity. So to convince ourselves, we can actually we can actually compute the spectrum of the Laplacian on the circuit. That's a very simple oscillation problem. So let's do that and see what we get. Any questions?
By Wiles law, by Wiles law,
Yes.
the lambdas do converge to zero with
No, no,
some
no.
order.
No, no, no.
Like not the product, but each individual.
No, by Wiles law, they go to infinity at a very at a speed that's controlled by the volume of the manifold. I'm an expert on that. I spent like 10 years of my thing doing these things for non-control. So Wiles law gives you the growth, I mean, that's a spectral geometry. But in this case, let's calculate it explicitly. So what we want to do then, to find the solution of this equation. Phi is a function on the circle, real value function on the circle, R, and phi is different from 0. Okay, so this, we know what they are. It's very easy. So a spectrum is actually, I mean, you can just solve this easily, that's not the problem, but sine and cosine function exponential IAT. So basically, the spectrum of delta, there is always 0, and then 1, 1, 4, 4. There are degeneracies, right? So degree 2, 9, 9, 16, 16. So basically, we can write it as 0 and n squared n equal to 1, 2, 3. But we understand that there is multiplicity here, multiplicity 2. Okay? So then, how we are going to multiply these guys? So that prime of Laplacian is equal to, yeah, I mean, we have to multiply like 1 by 1, 2 by 2, 4 by 9 by 9. I'm sure Euler wouldn't be afraid of this. Euler would compute it for us. But somehow it didn't come across this problem. It was not a problem he would be, I don't know, didn't come across this. So the definition, that's called zeta function regularized determinant. Zeta regularized determinant. This is actually due to Ray and Singer, mathematicians. In early 70s. So basically, they said that, yeah, this determinant Laplacian is equal to exponential of negative zeta delta prime at 0. It's this one. So let me now tell you what it means. So there's some notation involved. So what is this spectral zeta function? In order to make sense of that definition, I have to define for you, first of all, the spectral zeta function. Spectral. So this zeta delta of S of some variable S is equal to sum 1 over lambda I to the power S, lambda I different from 0 I, in fact, or positive. Okay, so what we're saying is that we just state that, okay, in our case, I mean, this is in general, in our case, this becomes actually equal to sum, actually becomes twice, right? It's twice because there's a multiplicity 2, 1 over n to the s, and from 1 to infinity on the circle. Right? And in fact, this is just the Riemann zeta function in this case. This is Riemann zeta. So for the circle, the simplest manifold, closed manifold, the spectral zeta function gives us up to scale a multiple of 2 Riemann zeta function. But in general, there is this function. And because of Boyle's law, that these lambda i's grow fast at infinity, fast enough, this function is always convergent in some right half plane. It's holomorphic. So let me put it for any closed manifold. So I have to be careful now. Closed Riemannian manifold. Riemannian manifold. The spectral zeta function, zeta delta S, is defined and holomorphic in real part of S bigger than half of the dimension of the space. That's we know, dimension of m, m, dimension of m over 2. So there is always now you may yeah, okay, I made a mistake here. You see, this statement is correct, but this doesn't fit with what I have here. You see, you didn't catch me. This is not n to the s, this is n squared to the s. Because the spectrum is not n, it's n squared. So it's 2s, right? But this 2 should remain for sure. So what is that now? So this is not Riemann zeta function. This is equal to zeta, this is equal to twice zeta 2s. So it's twice Riemann zeta function at 2s. Okay? And how I got my mistake myself, because this statement is true. And in this case, yeah. So this is a consequence of Boyle's law, as you mentioned. So Boyle's law implies that is true, because it gives you a growth rate of the eigenvalues of the Laplacian in terms of dimension of the manifold and volume of the manifold. Yeah. Okay. So it is holomorphic here, but beautiful thing is that it actually can be analytically continued to the complex plane. So the story goes on and can be analytically continued. Yeah, so can be analytically continued. To see, take away some points which are of the form dimension of m minus dimension of m over 2 minus s, where s is equal to 0, 1, 2, so on. So it can have at most poles at, well, there is certainly a pole here. There's definitely a pole here. This is dimension of m over 2. And we know exactly the residue of the function at this point is exactly related to the volume of the manifold. This is consequence of y as well, and covariant too. And then one by one, you go, and you always know that 0 is a regular point for this extension. So 0 is for the analytic continuation, which is going to be unique because this is a holomorphic function here. And 0 is a regular point. So the definition of Lagrangian that makes sense, because what you do, you just take this spectral zeta function, you do it, and then you just analytically continue, and you know that it's 0, it's regular at 0, and so the definition makes sense in the sense that it's well defined. But why this definition came about is something I'm going to explain now. That's not difficult to explain. What is the analogy here? But I have to say something else also. Hawking wrote a very famous paper after this paper of Lagrangian, where he used this idea to do some quantum gravity computations, actually. Euclidean quantum gravity. I mean, he really, there's a famous paper of Hawking which uses this thing, 1974, 75, after this. And of course, there are zillions of other papers that came after. So then I owe you now, before doing the computation in this case, I owe you the justification for this formula, right? Why this formula is correct. I mean, not correct. There's no question of correction, it's a definition. But why makes sense in some sense. The reason is not difficult, is the following observation. So let us define some function like C of S, which is equal to, well, let me put it like this. Yeah, I say C of S equal to 1 over lambda 1 S plus 1 over lambda 2 to the S, lambda n to the S. So these are a finite number of eigenvalues only. We don't look at infinite, just finite. And lambda I are strictly positive. Then obviously this is a holomorphic function in S, right? Obviously. And I want you to show that actually you can do that, that product of lambda I is equal to exponential of minus zeta prime at 0. You can prove this by just calculus. You have to remember how to differentiate lambda to the power S. You can use your knowledge of differentiate e to the S and then use. So this, yeah. So by analogy, so they said that, okay, we don't know this left-hand side, but everything on the right-hand side makes sense in the infinite dimensional case. So that's what Lagrangian proposed. And that's really a huge contribution because that's used in physics all the time. In mathematics, of course, all the time. A lot of things about these things, generalizations. But now let's go back to the circle case and see what is the determinant of our Laplacian. because there we have to say something. So here's an example. So I won't write down in terms of 2 zeta of 2s. So let's look at the zeta s, Riemann zeta function. So in this case, we want to compute 1 times 2 times 3 times so on, right? 1 times 2 times 3 times 4 times 5 times 6. So basically, this is infinite factorial, right? This is infinite factorial. Is equal to what? Is equal to exponential of minus derivative of zeta at 0. And this can be computed. I won't write the computation here, but this can be computed. I believe the result is root 2 pi. So yeah, you have this beautiful formula that infinite factorial is equal to root 2 pi. I remember I once gave a talk to undergraduates here with the title to be infinite factorial root 2 pi. It was announced everywhere in campus. A lot of people showed up, even from other students. They was, how come this could be true? I mean, doesn't make sense. So that I told them, look, I mean, you read these things in YouTube channels about 1 plus 2 plus 3 equal to minus 1 over 12, as we did last time. But this is even far more dramatic. You're multiplying all these things. Yeah, so, but the fact of the matter is that computing these determinants in general is much more complicated than computing values of zeta function. So this are, because there's a deep reason for that. It's not a local invariant. It's a non-local thing. So it's kind of difficult. But we don't have to. Okay, so this was a glimpse of. Okay, I mean, then for the Laplacian, then you can compute the determinant of. Okay, so let's compute now. So this gives us determinant of Laplacian exponential of, I mean, so we had the negative 2 zeta prime of 2s, so negative 4, then zeta prime of 0, right? Because this, the spectral zeta function here was 2 Riemann zeta 2s, right? If you want to take the derivative at 0 here, it's 2 times 2 zeta prime at 0. Okay, so the zeta prime at 0, we know that, yeah, so, okay, I mean, this is it. So zeta prime at 0 is equal to negative log negative 1/2 log of 2 pi. So I put it here, then negative, so exponential of twice log of 2 pi. So this becomes 2 pi squared. I mean, I hope I didn't make a silly mistake here, but this is essentially the idea. Because once you believe in this formula for Riemann zeta function, then you can derive the corresponding formula for the circle. Because the zeta function of the circle is not Riemann, it's just this one of it. Right? Okay. So now, yeah, this is the first step in this now we have a long list of analogies between actual quantum field theory and this Feynman diagrams that we are doing. So the next step is we have to think of what is B inverse. But B inverse is going to be the green function of the Laplacian with the inverse of the Laplacian. So this is going to be green function of the Laplacian. And how to decorate edges. I mean, so we put the green function, but then we have to come with a number. So this is just this is an operator, right? Or a function of two variables. A kernel of an operator is a function of two variables. One variable is here, one variable is there. But we have to integrate over the whole space for each edge. So this, if we get to this QFT at this, in one example, after we did the main thing, maybe just go back to that one. So it's all by analogies now. So any questions? Okay. So now we can turn the page. We can now start random matrix theory. Random matrix theory is much safer than statistical mechanics to study. And this guy said Boltzmann studied the statistical mechanics, committed suicide. And Ehrenfest started doing statistical mechanics, he committed suicide. And I said, now it's our turn to start statistical mechanics. Beginning of one of his lectures, this guy can't take things. It's our turn now to do random matrix theory, but there's no suicides in this, so it's all good stories. Okay, so this is now first steps in random matrix theory. It also goes by the name of matrix integrals. I mean, they're more or less same things. Okay. So what we want to do, okay, so let me introduce a space. Let Hn be the space of n by n Hermitian matrices. N by n Hermitian. Of course, complex, right? Complex matrices. So H, we just write as Hij is an n by n matrix. Because it's Hermitian, it only it's completely determined by values on the diagonal and above them. So basically what we have here is Hij is equal to Hji bar, right? Okay. Okay, the first thing we have to notice about this space is that this space is a real vector space. Because if you multiply by a real number, a Hermitian matrix remains Hermitian, not by a complex number. So, and in fact, its dimension is easy to calculate. Dimension of Hn over R is equal to, you want to guess? What is the dimension of Hn over R? It doesn't matter. It's just
it's n times n minus 1 over 2. Or
yeah,
n times n plus 1.
Yeah, you are thinking about maybe the real matrices?
Oh, yes.
These are complex? Yeah, thanks for answer, by the way, yeah. These are complex, so, I know you know the answer. You can calculate. This is n squared. So, I mean, let's look at n equal to 2. Such matrix is of the form here on the main diagonal is x11. Here is x22. Here off diagonal is x12 plus I, y12. I just use this coordinate y12. And here is x12. Sorry for that. This is x22, and here is x12 minus I, y12. So we have 4 parameters that completely fixes the thing. So this is x11, x22, the things on the main diagonal which are real, and the 2 components of diagonal only integrated. The one in the below is completely the conjugate of x12, y12. Okay. So in fact, you can use these coordinates in general and write down a linear isomorphism between Hn and Rn squared, Euclidean space Rn squared. There is a Lebesgue measure on Rn squared, which is product of all these variables, x11, x12, and so on. And then you can use this isomorphism to put a Lebesgue, analog of Lebesgue measure or integration measure over this space. And this we write it as dv of h, if you want. So this is product of dx I from 1 to n, product of dx ij, I less than j, and product of dy ij, I less than j. So there are n squared volume, differentials, one forms. Multiply them, you get this is a one form. This is an n squared form over this. Okay. Yeah. So now we define the so-called Gaussian unitary ensemble, or GUE. Gaussian unitary ensemble. Which is called GUE, is famous. So what we are going to do, we are going to multiply this by some Gaussian type function that makes it actually converge, because the integral of this is infinite over Hn. But we multiply by Gaussian, and we call this d mu of h, so we call it 1 over z. This is actually statistical mechanics, this ensemble notation. Exponential of minus 1/2 trace of H2 times dVH. And this trace of H2 is a function of matrices, of course, as you know. This trace of H2 is a quadratic function, which is what? Which is sum I and j, hij, hji, right? But hji, because we are doing trace, because you see, you multiply these things, you have to do one sum to get the diagonal element of the product, and then another sum to sum over all diagonal elements. You have a double sum. But we can switch now. That's equal to sum over I and j from 1 to n, Hij, Hij bar. Right? So now we can break this in two pieces, on the diagonal and off diagonal. So this is equal to, on the diagonal just comes sum xii squared. There's nothing else. And then on the off diagonal, there's twice, because above and below, they contribute twice on each. Sum xij squared plus y ij squared. Now I just go I less than j. I just wrote it in terms of independent variables. The independent variables are xij, and for I less than j, and yij, I less than j. These are parameters that parameterize this. Okay, so for us, I mean, the random matrix world or matrix integral world, this is like the analog of Gaussian, it's matrix Gaussian. Now, what is Z? Well, Z is integral of this guy over the whole space. dV of this over all the space. So when we divide by Z, we make sure that integral of d mu h, integral of this measure over the whole space is 1. So this is really a probability measure over a space of all n by n Hermitian matrices. So this is really is equal to 1. Okay. We don't need it, but it's a good exercise to actually, it's a quick exercise to actually compute Z, see what value we get actually for this Z. It's kind of fun. So it's not difficult at all because we have the expression here. In fact, well, so what is Z now? Integral over Rn, Rn squared. So we have got exponential of minus 1/2 sigma x I squared plus twice sigma x ij squared plus twice sigma y ij squared, right? VH. So then this is exactly like integral over r n squared exponential of minus 1/2 bx and x dx, where B now is this huge n squared by n squared matrix this time. You can see that it's really Gaussian. B is this huge n squared by n squared matrix, which has 1, 1, 1 in the first n coordinates, and has 2 actually after that. These are the xij coordinates, mixed coordinates. Not mixed, but xij coordinates. These are 1, 1, 1. So this, the remaining is n squared minus 7. Are you okay with this? Okay, but we have a formula of Gaussian, which is the value of this is determinant of root 2 pi over b, which in this case is going to be 2 pi. The dimension of the space d is actually n squared, so it's n squared over 2. divided by square root of determinant of B. Right? So then this is equal to, well, that's what it is here, 2 pi n squared over 2 divided by, now, of course, this is 2 to the power n squared minus n over 2, and times this one. So this is, well, there is this one that doesn't contribute, but this is 2 to the power n squared minus n over 2. Right? It's this number. So we get an explicit number, but it's really at this stage it doesn't matter. It's just for warm-up calculation. But the value of this, we just normalized it by that value, so that right. Right. Okay. Now, what we want to do next is to find the correlation, pairwise correlation functions for this. So, to see what those values are. And then we'll apply Wick's theorem in this case to start the graphical calculus for matrices. I'll just write this lemma, and then on Monday we come back to this. Finish. So this is the last part. So this is the lemma. Lemma is that Hij, the expectation value of Hij times HKL is actually equal to 1 if J equal to K, well, first of all, I equal to L this way, and J equal to K, and is 0 otherwise. I mean, proof of this. Okay. Of course, the expectation value, we know what it means. It means that we multiply. So, I mean, if you remember, Hij, HKL is equal to, by definition, 1 over Z integral of Hij, HKL. Okay, so I don't write that exponential anymore. I just write d mu of H, right? But remember, this is now Gaussian, matrix Gaussian volume form, and we want to compute this. Okay. But Hij is just Xij plus root minus 1 Yij. Right? So for this, to compute this, I have to compute the correlation functions between x's and y's and xy's. Right? Okay, so back to Euclidean case, back to original formula. We saw that in general, I mean, if you have a Gaussian like this over our n as or d actually we had before, minus 1/2 bxx dx. For this, we had that xi xj is equal to b inverse ij. You remember this formula that in preparation for Wick's theorem we prove this first by introducing source term and this. So now we are going to apply this to this B that we have here. And then we get the following. That actually, for example, xij, I mean, xij exactly is equal to, I mean, this is completely diagonal situation, right? So is equal to, okay, so let me put it this way, xii times xjj is equal to 1 if I is equal to j and is equal to 0 otherwise, right? From that thing over there, you know. And also xij, oh, so sorry, yeah, in fact, xii and xkl is always equal to 0 for all I and k less than l. Again, similarly for xii, ykl is equal to 0. Similarly for this. And you can also write correlations between xij and xkl for I less than j. And I mean, there is also similar formula like xij, xkl is equal to 1 only if I is equal to k, j equal to l. You have I less than j, k less than l, and so on. So you can write correlation between these coordinates. Now we want to write correlation between complex coordinates. That's the thing. So let's do one of them and verify this. So I'm just going to verify this statement. I mean, for example, let hij, so assume I is less than j. Let hij in this case is xij plus root minus 1 yij. And let's compute also hji, which is equal to, right? I mean, here you're saying, okay. All right, so you know what? I'm going to leave this to you guys to do as a fun lemma. So I'm getting tired. And we have spent already 20 minutes. We have 20 minutes over regular time. So use those formulas. To finish the proof. Is there a simpler proof here? I like to think that there's a simpler proof, but I don't see how. I want to reduce everything to this real case, real parameters. But you know, in general, this is a very bad idea, right? It's like in complex analysis, if you want to solve problems completely, you write it in terms of the real and complex parts. This is a wrong start always. You have to stay within complex parameters all the time. Here also, it's always good to stay, but okay, but I don't see that proof yet, but at least this, it's kind of longish because there are many things to check in this case, but this is the core calculation, really what's needed now. So then we'll see that there's a relation between this and Riemann services. Yeah. it's going to come. So this is this advertisement for coming attractions. Okay. So thank you very much. There are no questions in the Zoom. I just say thank you and I see you on Monday. And thank you all. So yeah, so feel free to contact me about projects or anything else you want. Thank you.